Good morning. It is 10:09 a.m. Eastern Standard Time on Thursday, August 24th, year 2023. We are going to invest a couple of episodes in just doing a reading of the Yale Law Journal article called The Antibody Patent Paradox. We have a full copy of this available on, you can find it under the research on Houstonic Live, which is houstonic.live, which links back to houstonicits.com, but it's under the A's. And if you scroll down, you will see the antibody patent paradox. This is a fairly recent article, February 2023, out of Yale Law, in the Yale Law Journal, February 2023, written by Mark A. Lemley and Jacob S. Shurkow, Sherkow. It's 75 pages, lots of content here. I just thought that for those of you who are, again, working in the yard, working outside, it's an opportunity to have it narrated. I think it is important. I think it is important that we continue to continue to remind people how important this topic is. And again, it's not just because patents help companies protect the opportunity to make money. That's not really what's going on here. It really highlights how much is unknown still with respect to genetics, respect to the human genome, how it functions, how proteins are expressed, etc. And it provides clues as to the types of technologies that will be rolled out over the next several years, and that probably already have been rolled out to some extent, and why. So without any further ado, let us just get straight into it. So the abstract. Antibodies constitute a staggering $145 billion annual market, an amount projected to almost double by the year 2026. Consequently, patents covering antibodies are among the most valuable in the patent system. But antibody patents are being struck down left and right, victims of the Federal Circuit's recent shift to strengthen two doctrinal areas of patent law: enablement and the written description requirement. For each, the Federal Circuit has heightened requirements that patentees disclose or teach how to make and use the, quote, full scope, unquote, of their inventions. There are good reasons to be skeptical of the Federal Circuit's attack on genius claims in chemistry generally, but it seems to be a particular problem for antibodies. Applying the Federal Circuit's reinvigorated written description and enablement requirements to antibodies and their chemical structure fits poorly with the science underlying the molecules themselves. Immune receptor protection, a semi-random and galactically expansive response, produces antibodies that are startlingly different in both structure and function. There is no way to describe genius claims to antibodies that satisfy the court's current tests. The science simply doesn't allow it. At the same time, this change in the Federal Circuit's jurisprudence is a legitimate reaction to some of the problems with the long-standing and long-permitted practice of claiming antibodies in functional terms. Functional claiming can lead to overbroad patents that stifle future innovation, as it has done in the software industry. Perhaps the Federal Circuit is wary of a similar result in biotechnology. Fortunately, we think there is a middle ground. A new, or really quite old, form of patent claim drafting would give inventors effective control over true substitutes without giving them the power to block real improvements. Means plus function claims and infringement by the equivalents. These doctrines limit patentees to claiming only the specific structural features of antibodies they both possessed and described, but also entitle them to assert their patents against antibodies with equivalent functions but different structural characteristics. If the economics of intellectual property center on balancing a need for protection beyond the literal invention with a desire to allow improvements, this seems a step in the right, or at least in a doctrinally permissible and economically sensible direction. Whether patentees go for such a solution remains to be seen. Recent empirical evidence on antibody claims has yet to document such a shift. Patent attorneys may need to get over their historical reluctance to writing their claims in such a fashion. Our solution won't give patentees everything they want, but they might just find it gives them what they need. Sort of like the Rolling Stones song, I suppose. All right. So that is the abstract. So the introduction. Antibodies are the backbone of modern biotechnology. They are the workhorses of molecular biology research, the principal component in numerous diagnostic tests, and the heart of both the immunity provided by COVID-19 vaccines and the single most effective COVID therapy. Narrator's note. All right, clearly that's what the article says, right? And that's how it still needs to be pitched. I'm not saying I disagree with it, just highlighting that's the way the article has to pitch it. Hence, the importance of the of people believing the narrative, the effectiveness of the medications. Long before antibodies became a household word during the COVID-19 pandemic, engineered antibodies were central to many of the most important and most valuable medical tests and therapies of the past 30 years. Annual revenue from just the top 10 best-selling antibody drugs in 2019 reached $79.1 billion, almost double that of the global market for movies and music combined. Patent law has long given antibodies broad protection, allowing an inventor who identifies an antibody that targets a particular antigen of interest to claim ownership over not just the particular antibody they developed, but over a genus of antibodies attracted to the same antigen. An inventor who created an antibody that bound to, say, tumor necrosis factor alpha, or TNF alpha, the basis of 3 of the 6 top-selling antibody therapies, could claim that antibody and almost all other antibodies that bound to it. In part, this claim practice was one of necessity. Unlike typical, quote, small molecule, unquote, drugs, scientists had long identified antibodies not by their precise molecular structure, but by what they did. Sort of like if someone invents an airplane, should they own, I don't know, you can't really patent an airplane, but just bear with me. Can they patent everything that flies? Still gets you there, right? Indeed, characterizing antibodies atom by atom was both impractical and pointless, akin to describing a fighter jet by just listing every nut and bolt. Functional claiming, or I should say, quote, functional claiming, unquote, the ownership of any device that performs a function was not only permitted, but a norm for antibody patents. The form of patent claims thus followed their function. So narrator's note, so you can see the absurdity of this, right? Antibodies have not been patented by their form. They've not been patented by their molecular design. You would think they would have been patented by their molecular design. That's the way you would think about it. If someone would patent, I don't know, I don't know. I don't want to say pain med, but I don't know what else to say. I don't know, something that helps with toothache. You would think, oh, it's a specific chemical. Presumably remdesivir, a specific chemical formula, could be patented. But why not antibodies? If we can patent chemicals that we put into our bodies, why not antibodies? Well, let's continue on. By the way, I copied all the footnotes in here as well. I'm not going to be reading the footnotes. Things have changed. In the laboratory, it is now easier to identify the physical sequence of a newly discovered antibody. But at the U.S. Court of Appeals for the Federal Circuit, no antibody patent in over a decade has survived the challenge based upon overbreadth and inadequate disclosure, with the court regularly throwing out billion-dollar jury verdicts in favor of those patents. Mainly, the patents have fallen victim to patent law's written description requirement, the doctrine that requires patentees to disclose enough examples of what they invented to show a, quote, person having ordinary skill in the art, something which is the acronym is PHOSITA, person having ordinary skill in the art, or a reasonable expert, that the inventor was in possession of the invention. That doctrine is intended to prevent a patentee from gun jumping, which is filing for a patent application before they have actually nailed down their invention. Emboldened, perhaps, by this expansion of the written description doctrine, the Federal Circuit has also invalidated antibody patents on the related doctrinal ground of enablement, even though the technology is now easier to find and apply. Because the written description doctrine prevents inventors from filing patent applications too early, the doctrine has long operated with the conceit that the more knowledge a person of, let me get this acronym right, a person having ordinary skill in the art possesses about the field, the less a patent must show to demonstrate possession of that invention. With antibodies, however, a paradox has emerged. In the early days of the industry, when scientists often knew little about the precise molecular and genetic structures of antibodies and lacked tools to easily find them, the law permitted broad patents covering any antibody that bound to a particular target with a certain specificity. Identifying those characteristics was the only practical way to describe the newly discovered antibodies. Now that scientists understand the chemical structure of antibodies better, including an appreciation for just how genetically diverse antibodies are, even those that bind to a single target, functional antibody claims to antibodies' antigens are routinely being held invalid for failing the enablement or written description doctrines. Today, scientists know that discovery of one or even dozens of antibodies that bind to a particular target with a particular specificity doesn't exclude the possibility that many other antibodies with different structures do the same. Instead of requiring scientists to disclose more information when their colleagues start out knowing less, patent law now requires them to disclose more information about each invention when their colleagues know more. This development cuts against patent law's precept that, quote, there is an inverse correlation between the level of skill and knowledge in the art and the specificity of disclosure necessary to satisfy the written description requirement, unquote. We call this the antibody patent paradox. So previously, in summary, perhaps wording it more simply, patents were more broad because people knew less. It was assumed that we knew less, we could measure less. Now we can measure more. Now we supposedly know more, right? We can describe things in chemical, but also we have realized that there is no one antibody. We know that there's not just a few antibodies that work. We have now discovered that there are thousands or potentially millions of different chemical structures of antibodies that may work against one particular antigen. It's a huge number. Why would such a huge number exist? Why? It is a representation of the different ways something that we would make an antibody to can present itself. And it also suggests that there's a huge diversity in the human population, all right, of how the antibodies are made. How many times have you heard the spike protein? The spike protein, as if there is one and only one way in the entire galaxy to make a spike protein. Do you really think that every single spike protein made by every single person is exactly, precisely the same? No, of course you don't. You probably never thought about it. Similarly, there is the antibody challenge. Where do you really think that every single person is going to make exactly, precisely the same antibody chemically to a spike protein? Well, first of all, there's a huge diversity of these proteins, which the body is being instructed to manufacture by the new era of vaccines. But also, there's great diversity in how people will manufacture those antibodies. So we have this huge range right now. So at the same time, we're saying, well, we need to be more precise. Now we discover that there's a huge range of potential antibodies and ways that they could be manufactured. So it goes against the tradition. I'll read this again. It's a fantastic paragraph. Because the written description doctrine prevents inventors from filing patents applications too early, the doctrine has long operated with the conceit that the more knowledge a person having ordinary skill in the art possesses about a field, the less a patent must show to demonstrate possession of that invention, right? So the more knowledge a person having ordinary skill in the art possesses about the field, the less a patent must show to demonstrate possession of that invention. With antibodies, however, a paradox has emerged. In the early days of the industry, when scientists often knew little about the precise molecular and genetic structures of antibodies and lacked tools to easily find them, the law permitted broad patents covering any antibody that bound to a particular target with a certain specificity. Identifying those characteristics was the only practical way to describe newly discovered antibodies. Now that scientists understand the chemical structure of antibodies better, person having ordinary skills in the art, functional patent claims to antibodies antigens are routinely being held in invalid for failing the enablement or written description doctrines. Today, scientists know that discovery of one or even dozens of antibodies that bind to a particular target with a particular specificity doesn't exclude the possibility that many other antibodies with different structures do the same. Instead of requiring scientists to disclose more information when their colleagues start out knowing less, patent law now requires them to disclose more information about each invention when their colleagues know more. This development cuts against patent law's precept that, quote, there is an inverse correlation between the level of skill and knowledge in the art and the specificity of disclosure necessary to satisfy the written description requirement. We call this the antibody patent paradox. The antibody patent paradox may be brought a part of a broader shift in patent doctrine, what one of us has called the death of genius claims. Or it may be an extension of the concerns about the abuse of functional claiming in other areas like software. Or it could be the result of trying to fit one of the most complex biological molecules we know in the single convoluted sentence that a patent is that sentence that is a patent claim. Or perhaps it is simply the result of a circumstance in which the more we learn what we don't know. We explore all of these possibilities. And I like this one here. It is the result of a circumstance in which the more we learn that we don't know. And I like that sentence. It highlights that, yeah, we know that there is DNA. Yeah, we know we've mapped out the human genome. But the more we learn, the more we realize, well, the genome is just, how many copies of it are there? How many different copies are there of it in the human body? How many cells have subsets of it? When we make antibodies via ribosomes, how are those ribosomes functioning based upon inputs, a variety of inputs? There are so many factors here that we didn't think about before. We just thought, oh, DNA is just the DNA. It's just the code you run. But in reality, it's so multi-staged how machines are built out of this. And the more there are more and more systems cooperating with each other, so that the more we have learned, the more we realize we don't know. There are just so many checks and balances and methods of communication within the body. Regardless of the explanation, the antibody patent paradox lies at the heart of several critical questions in patent policy. How broad patent claims should be to encourage invention, whether patent law is and should be technology specific, and how we accommodate follow-on innovation after an initial pioneering disclosure. If we get those questions wrong, we could end up with a second paradox: how the patent-fueled success of antibody technology made it impossible to get the very kinds of patents that drove innovation in the first place. As a matter of innovation policy, we think the end of functional antibody claims is a problem, but the likely effects on innovation are complicated. We suggest some possible middle ground that might save narrower antibody genius claims. In part 1 of this 80-page essay, we explain the science of antibodies, how it has changed, and why antibodies are so complex. In part 2, we discuss the parallel history of the law, beginning with broad protection for functional antibody claims and ending with the current period of hostility to antibody patents. In part 3 considers several possible explanations for the shift, none of which are completely satisfactory. In part 4, we explain how the antibody patent paradox is central to many of the current policy debates in patent law. We offer some guidance as to how to resolve the paradox. We conclude by suggesting broader implications for the written description doctrine and patent claims for other complex technologies. So before going further on this topic here, it's not just antibodies which are a problem. Okay, there's in addition to, it's the whole patent system and its implementation and compatibility with technology and implementation. Also, it is the challenge that and again, this is speculation, if there is a bigger agenda to shape medicine from one being simply to providing care to also collecting data. All right. If this discussion starts to expose just how much is unknown. The other part about this, somewhat unrelated to, having to read the document, is, well, we can better understand the ecosystem of individuals who have been involved with public positions of, let's just say, social media influence, by understanding just how important this topic is. What led us to this, okay, was a 2011 decision, which I believe this, of course, will refer to, which has been described as one of the most impactful rulings on patent law in quite a while, and it has to do with patenting of proteins. And it was a case between a company which was called Centocor, Centocor, and was it with Centocor versus Regeneron? Stupid me. Now I'm getting there's so many different companies in this space, I'm getting them mixed up. And it was about effectively antibodies, okay? And the one of the chief lawyers on that case was a Les Weinstein, L-E-S, and last name Weinstein, who's the father of Brett Weinstein, who we know from the Dark Horse podcast, and his massive influence, which seemed to have just come out of nowhere just in time for the pandemic, and also the father of Eric Weinstein. And as we've shown in other shows, other episodes of Houstonic.live, Eric Weinstein made a huge chunk of change, providing consultation for the personal investments of Peter Thiel. And much of those personal investments, surprise, surprise, were biotechnologies. And many of those, in turn, were actually antibody companies. Some of them are up in Vancouver. Now, the Les Weinstein story, he happened to be a patent lawyer who was the very first patent lawyer in U.S. history hired by the United States Department of Justice Antitrust Division, and was involved all the way back in 1962 in a case, or I should say, in the investigation of Estes Kefauver's, a senator from the state of Tennessee, a bill that he was trying to pass called the Drug Industry Antitrust Act. And just in time for that whole debacle to be resolved, suddenly there was this huge awareness of something called thalidomide causing serious birth defects in Europe. And Les Weinstein was involved in that and a variety of other cases since then, and all related to patent law. But now as an independent arbitrator and sometimes still practicing attorney, he's still been involved in these cases. Seeing that Eric Weinstein and Brett Weinstein, for reasons that have remained mysterious to most people, just were foisted upon us as the faces of rational thought, it made us wonder, well, why? We dug in. We look at their Wikipedia pages. Neither one wants to talk about who their father was. That's always a clue. When something so basic is omitted like that, and we figured out, wow, okay, so their father's a lawyer. The fact that the father's a lawyer is not a crime. The fact that their father made some good money as a lawyer is great. Good for them. It's the fact that there's only, you could probably count them on your fingers, even if you had one chopped off, or two, how many lawyers have been so key to the history of patent law and biotechnology, and in particular, this topic such as antibodies. And given the fact that Les Weinstein was appointed by JFK into that role and has, just look at his own profile all the way up to the Centocor case. Wow. It was Genentech, Centocor, Genentech. Now, these companies have been repurchased, so the title of the 2010, 2011, 2012 case has changed based upon acquisitions. But, and then it goes, okay, so if these are some of the most important rulings of the last 20 years, and knowing that this topic can help us be a lens through which we can help understand a lot of stuff what's going on. Now it makes sense why Brett Weinstein and Eric Weinstein would have become trusted voices, social media influencers, and so on. Now it makes sense. And it's odd that so many other, B-grade people who have also become social media influencers on different platforms seem to have just spawned out of chat groups started by Brett Weinstein, for example. So it is a big part of the machine. While there is, it's not the only thing you should be looking at, I would go far as to say that if you are trying to understand, if you and your peers are trying to understand what's really driving the current pandemic, if you are not hearing about this topic, you're either being misled or you're not listening to people who can see a bigger picture. And if you're told that it's not important, you are definitely being misled by people who definitely know it is important. So let us read. We're 33 minutes in. I don't want to go over an hour. So let's start with the first section here, the science of antibodies. Trying to think, should I just go for it? Yeah. Antibodies in the immune system. The human immune system is dynamically adaptive. It can respond in real time to both unknown and unforeseen foreign invaders, like novel pathogenic bacteria and viruses. There's that novel word again. The key to this adaptive immune system is the body's ability to quickly and precisely flag such threats as potentially harmful, even though the immune system hasn't encountered them before. Once a threat is identified, the immune system also needs the tools to neutralize and dispose of it without harming healthy tissue or commandeering too many of the body's resources. An over-aggressive immune system response risks harming the body by attacking foreign but benign material, while an apathetic immune system response risks yielding the body to systemic infections. Functional, adaptive immune systems must therefore be precise without sacrificing flexibility. The marriage of precision and flexibility is largely mediated by a class of complex proteins known as immune receptors, specifically antibodies, and T cell receptors. These immune receptors are produced by two types of immune cells, B cells and T cells for antibodies, and T cell receptors, respectively, that circulate throughout the blood and the lymphatic system. Antibodies and T cell receptors jut out from the surface of their respective cells until they eventually come in contact with a complementary large molecule known as an antigen. If recognized as a foreign substance, this contact causes the particular immune cell carrying the immune receptor to both proliferate, that is, divide and make copies of itself, and signal other components of the immune system to bind to the offending material. The upshot of this interaction is that more immune receptors specific to the particular antigen will be produced, and that interactions between B cells and T cells will allow the body to remember the offending antigen if it attacks the body again. In this way, the immune system can continually adapt to new threats without entirely forgetting past battles. Importantly, antibodies and T cell receptors are not monolithic proteins. To the contrary, they are incredibly diverse, with a given individual likely having tens of billions of different variations of immune receptors circulating in their blood at any given time. This poses a genetic conundrum. How can so many different immune receptors be made without the genome, the sum total of DNA in an individual, being infinitely long? Great question. The answer lies in how immune receptors are made. Antibodies, for example, consist of 4 chains of proteins, 2 heavy chains and 2 light chains that come together in what is classically represented as a Y-shaped structure. The tip of this Y-shaped structure, known as the complementarity determining region, hopefully I'm pronouncing that right, first time I'm encountering that word, CDR, are the portion of the antibody that interact with the antigen. Both of these chains are produced, incredibly, by only 3 genes, V, D, and J, each of which contain multiple smaller cassettes. For example, V1, V2, V3, and so on. Naive B cells that have never come into contact with an antigen, randomly combine these cassettes from each of the 3 antigens and then further alter the genetic makeup of the combination, producing a novel antibody. T cells create their receptors through a similar mechanism. This random recombination system has the potential to produce almost limitless number of different immune receptors. Some researchers have estimated that the theoretical number of different types of antibodies, for example, is on par with the number of stars in the galaxy. Antibodies' galactic diversity means that multiple different antibodies are likely to target the same antigen, albeit in potentially different ways. Multiple antibodies specific to a particular antigen may, nonetheless, bind to it in different places. The specific place on an antigen to which an antibody binds is known as the epitope. Even multiple antibodies specific to a single epitope may bind more or less strongly to it, an antibody's affinity, if you will, in immunological parlance. And even multiple antibodies with similar epitopes and affinities may nonetheless possess differences in how stable the interaction is. That is, how long the interaction lasts, a measurement of an antibody's avidity, A-V-I-D-I-T-I. Because antibodies are produced through the VDJ recombination mechanism, however, all have different genetic sequences, which is to say, that at a molecular level, all antibodies are different. Immune receptors are of immense biological value, the central feature of the adaptive immune system as a whole. This is because the CDRs, and again, going back to what we read earlier, the CDR stands for the complementarity determining region. Going back here, this is because the CDRs of antibodies have the potential to bind to almost any other large molecule, extant or yet to be conceived. Excuse me. But the interaction of any particular CDR is incredibly specific. Generally speaking, each antibody binds to only a single epitope. Scientists have long likened this specificity to a lock and key model, whereby an antibody can be unlocked by only a single epitope on a single antigen. Today, researchers appreciate that there is some fuzziness to this lock and key model, more accurately describing CDR binding as an induced fit. But even with the molecularly large antigens, antibodies can recognize atomic and in some cases subatomic differences in epitopes. As noted above, this pairing is not unique. A given antibody can bind to only a single antigen. Let me restart this. As noted above, this pairing is not unique. A given antibody can bind to only a single antigen, but a single antigen can, and frequently does, bind with multiple, slightly different antibodies. To extend the lock and key metaphor, while each antibody is specific to only a single antigen key, any given key can unlock several and often many antibody locks. While exceptions to this lock and key model do exist and are the subject of ongoing research, this specificity is a hallmark of immune receptors and a few other biologic molecules that have similar properties. I'll try the next section here. Applications of antibodies. Antibodies' specificity makes them useful in multiple applications, including research tools, therapies, and diagnostics. As research tools, antibodies are the workhorses of any molecular biology lab. Among the most frequently used tools in basic science research and in clinical assays. Antibodies can be used, for example, to assess whether a specific antigen exists in a large mixture of proteins, like a powerful magnet to find a needle in a haystack. Narrator's note here, there's another article from the Health Institutes out of England that we also need to read. I've highlighted a few sections of it. It states that much of the early research on mRNA was actually done not because there was interest in mRNA as a in and of itself or in the cell-to-cell messaging, but they found that study to be necessary to better understand antibodies. And this is interesting because one of the main technologies that we know of anyways, that has been rolled out during COVID has been mRNA, which cause cells to express these proteins, which in turn cause, as we are told, antibodies. It does make one wonder if one of the reasons this tool of mRNA was used was because humans are now being used directly in their natural habitat to study the production of antibodies, as opposed to just doing things out of a dish and with a few volunteers and using animal models. Pretty dark speculation, but something to consider. Back to the article. This also, I'm gonna go back a couple of sentences. As research tools, antibodies are the workhorses of any molecular biology lab. Quote, among the most frequently used tools in basic science research and in clinical assays, unquote. I'm just so surprised to read that. And there is no, it's just, I would not have expected it. I would have expected, oh, the antibody guys are over there in the corner and they're just doing all the immunology stuff. I did not know that antibodies themselves were tools of great interest. Antibodies can be used, for example, to assess whether a specific antigen exists in a large mixture of proteins, like a powerful magnet, to find a needle in a haystack. This also allows researchers to isolate a specific protein from an undifferentiated mass for further study. Researchers can further modify this technique to assess whether one protein interacts with another or whether a given protein interacts with another molecule of interest. This includes research into how certain proteins or other large molecules bind to DNA, instrumental in investigating how genes function. Antibodies can also be used to separate living cells from one another, giving researchers the ability to investigate molecular and genetic changes at the level of individual cells. The use of antibodies as research tools is a large market unto itself, clocking in at $3.4 billion per year in the year 2020. 1 second here, just need to check a text message. Relatedly, antibodies can also be used as diagnostics for diseases or other health conditions. A diagnostic technique known as immunochromatography, for example, pairs antibodies with fluorescent or other color-providing molecules so that they glow when they come into contact with a particular antigen. This is the principle behind some of the most popular at-home diagnostics for COVID-19, such as Abbott Laboratories' Binax Now test, which uses antibodies tagged with a color-giving fluorophore to test for the presence of a protein in the shell of the SARS-CoV-2 virus. So, you take those tests and you swab the nose, you swirl it around, yuck, and then you put it in and then it turns a color. This is what's happening. Immunochromatography. Third time. Immunochromatography. Bingo! Immunochromatography. Woohoo! Got it. Immunochromatography. I'm just going to be like making songs out of it right now. So, remember that time I told you about? Exactly 72 hours. I had a severe case of COVID 72 hours after I left the Children's Health Defense Conference. I took the test, and it was like the scene from the movie Thing, where you take the hot wire and you dip it into the blood, and it jumps out. It was a little bit like that, almost as if I was hit with a clone or something like that. It was just so shockingly positive, and eventually I got over it, right? Lots of water, a little bit of rest. I did use some of the IV mech-y stuff to take an antibiotic, food, and it goes away, right? You flush it out of your system, the garbage. But that's how that technology works. A variation, getting back to this, a variation on the technique tags the antibody not with a fluorescent molecule, but with an enzyme that detectably reacts when the antibody is bound to it. A technique known as enzyme-linked immunoassay, or ELISA. that ELISA. Enzyme-linked immunoassay. That's what the ELISA test is. This is the primary technique used to detect a number of diseases, including influenza and rotavirus. Other diagnostic tests. Sometimes I think I missed a couple of the plurals when I copied this in. Other diagnostic tests. Okay. Other diagnostics test for the presence of antibodies themselves in the blood to determine whether a patient has been exposed to a particular infection. Antibodies can be used to detect the presence of certain proteins typically produced by cancer cells, an important technique in cancer diagnosis known as immunohistochemistry. Like research tools, antibody-based diagnostics are big business, yielding their manufacturers roughly $23 billion a year. Antibody specificity also makes them useful as therapies. By binding to particular antigens in the body, antibodies can precisely target certain cellular pathways gone awry. The cellular protein tumor necrosis factor alpha, or TNFA, for example, is responsible for driving a powerful inflammatory response. Antibodies that bind to TNFA, or alpha, again, that's tumor necrosis factor alpha, also known as anti-TNF alpha antibodies, in turn, disrupt this pathway and are immensely useful in regulating an overstimulated inflammatory response. This is the mechanism of 3 of the top-selling antibody therapies in the world, from Humira, Enbrel, E-N-B-R-E-L, and Remicade, R-E-M-I-C-A-D-E. Antibodies can similarly be used as therapies to signal biologic targets to other systems in the body, including other components of the immune system. Modified antibodies that precisely target vascular endothelial growth factor A, or VEGF-A, a protein known to be overexpressed in certain cancers, can be used to recruit other components of the immune system to attack the offending tumor. This is the basis for 2 antibody therapies currently on the market: Avastin, A-V-A-S-T-I-N, and Lucentis, L-U-C-E-N-T-I-S. Lastly, antibodies can be used to precisely target certain cells in order to deliver drugs chemically attached to them. These antibody-drug conjugates are designed such that their CDR region is specific only to a certain cellular antigen, while their tail, or, quote, constant region, unquote, is attached to a therapeutic drug. When the conjugate binds to a target cell, it is effectively eaten by the cell and subsequently releases its drug payload. This is the basis for the breast cancer therapy Enhertu, E-N-H-E-R-T-U. All right, I think I'm going. Let me just see how much more is here. Okay, so I think I'm going to wrap it up there. So we're going to start off the next section, the history and development of antibody research. Perhaps later. I have to step out right now. I think this is a good start. I don't want any particular section to be more than an hour. I think that's. I think we'll break it up like that way. And for those who are interested, starting in a few minutes, I'm going to begin playing where we left off on the book Gene Machine by Venki Ramakrishnan, Deciphering the Secrets of the Ribosome. It's a pretty technical book, lots of names in it. I thought it would yield a little bit more in the area of highlighting how much is still unknown. It's not giving me everything I thought it would, but we're already more than halfway done with the audiobook, so might as well listen to the rest of it. I still stand behind the statement that Venki Ramakrishnan is a very important person. Again, this isn't conspiratorial type talk, but just in advancing the state of the art of what is known about the ribosome and how important it is to understand that machine, because knowing that machine helps us understand how other proteins are made. These antibodies, this is the antibody patent paradox. These antibodies are proteins that are made by, guess what? Ribosomes. It may seem like we are going in a lot of different directions here. Like what everyone may be talking about a particular health freedom thing, but we're talking about patents, talking about antibodies. We're talking about studying the ribosome. We're talking about the big data, which is going to be potentially required for reverse engineering these things. And the other thing that I've been speaking a lot of is protocols. I have a vision on how these things are all going to be working together, and we're still going to keep doing the history stuff on this as well. Amazing backgrounds that we've been able to dig up on this company, CentoCore, which is so crucial to this topic. In fact, this next section here talks about Jorges Kohler and Cesar Milstein. These are the two main people that Health Institute's paper out of the United Kingdom speak about. These are two key characters. And one of the main people that effectively stole a lot of intellectual property to make a synthetic antibody, or clone an antibody, back in the 1970s to be the key person starting his own company, was Hillary Kaprowski out of the Wistar Institute. And that company was CentoCore. Hillary Kaprowski, one of the same three people involved in the polio vaccines. Hillary Kaprowski, who did he mentor? He mentored Stanley Plotkin. He mentored Paul Offit. And there was also Dave Weiner. And Dave Weiner is a co-founder of what became Viral Genomics and then Inovio. Stanley Plotkin was a senior scientist at Inovio with the EROS, the Tuberculosis Vaccine Foundation, and is a highly respected person of the CEO and founder of Vical, Vijay Samant. This ties into what? Some of the key people who are still advising us today, in particular Robert Malone, who got his big start at Vical, and although he was not a co-founder of the Viral Genomics core of Inovio, he was involved in the founding of Inovio AS, which was a Norwegian company, I believe, that was using electroporation to create immune responses. So again, in that direction as well, the scientists, which we see scientists, and Malone is, although he's more in the business end of things, he does have a PhD. That is the area where he probably has subject matter expertise on. In fact, he does. And the reason why he is in a position to speak to a lot of these topics is because he knows what's going on behind the scenes. He knows about patents. Malone knows about patents. He knows about antibodies. He was involved with Inovio. He knows the role that CentoCore had with antibodies. He knows about the role that Kaprowski has. And it's no surprise whatsoever that his big breakthrough, as far as social media goes, was on the Brett Weinstein podcast, the Dark Horse podcast. The son of the lawyer that represented, it was in that CentoCore case about antibodies in 2010 to 2012. This is where it's at. Forget about your fifth generation warfare nonsense. This is where it's at. We're figuring it out together. It's exciting. So with that said, back to work. We have big things to do around here. A few minutes down, and then we'll come back. The main channel right now is on strike, so we're not going to be able to use it for a little while. Thank you, everyone, for your support. Please have a wonderful day. Stay positive. Keep learning. Keep expressing those proteins. Put those protein shakes, protein machines to work all over the place. And God bless.